Have you ever had to replace a transistor with a different one? Replacement charts can be hit or miss. So today we're going to learn how to pick a replacement that will work correctly. Hello and welcome back to Noel's RetroLab. Sometimes you need to replace a transistor on an old board, but you find that that particular transistor model isn't available anymore. That usually means that the transistor stopped being manufactured a while ago and it probably wasn't very popular to start with. That exact situation happened to me a couple of weeks ago when I was building this Amstrad CPC replica board, but it can also happen when you're just repairing a board and you need to replace a faulty transistor. So how do we find a suitable replacement for the original transistor? We can look it up on a replacement table, buy the new one, and done, the end. Or maybe not. That might work, but at the same time, it may not, like it happened to me last time with the Amstrad CPC board. I first thought I would make a quick video explaining how I picked a replacement, but the more I researched it, the more interesting it got. And so I kept going down this rabbit hole. So today we're going to do a deep dive, learning more about transistors and what to look for when you need to replace them. Transistor equivalence tables are often okay until they're not. The problem is that transistors are just very complicated components. We may think of resistors as really simple components, but they're actually more complicated than that. They have a resistance, max current, tolerance, temperature variations, etc. So it's just that we tend to think about the ideal resistor that just has one perfect resistance value. If resistors are complicated, imagine transistors. They can be characterized by a lot of different parameters, starting by the type of junctions it's made of, to all sorts of nonlinear details like current flow through terminals, amplification parameters, and frequency responses. You just need to have a glance at a data sheet for a transistor to make it very clear that those are some seriously complicated components. The danger with using an equivalent table to pick a transistor that is close enough is that it may be close enough in many of those parameters, but not in the one that really counts for the circuit is being used in. So unless you're getting an exact replacement with all of the same parameters, the safest approach is to look at the circuit where it's being used and try to understand its exact role in there. That's because transistors are used for all sorts of things, to act as switches, to amplify signals, to stabilize current flow, to turn signals into digital signals, or to perform all sorts of operations on them, especially once you combine transistors together. A lot of the transistor magic is already happening inside each integrated circuit, so we don't usually have to think too much about this, and instead we can focus on the high-level behavior of the chip itself. But when transistors are loose in the board like that, then we really need to pause a moment and make sure that we understand them. So let's have a look at the transistor that I have issues with on the Amstrad replacement board. This transistor is placed between the clock signal that the gate array generates and the input clock signal for the Z80. Can you tell what it's doing at a glance? If you're like me, it may not be immediately obvious. Because transistors are just complicated, I often have a hard time getting a feeling for what exactly they do in certain configurations. Which is particularly frustrating to me because I have a degree in computer systems engineering and I had several classes on the topic, but the emphasis was always on deriving equations to get an exact analytical solution for the behavior of the transistor. I got so drowned in details of equations, nonlinear responses to different frequencies and currents that I lost sight of the big picture. So let's figure out what this is doing at a really high level. All transistors have three terminals. There are different types of transistors depending on the technology they use, BJT and MOSFET being the two most common ones. This one is a BJT, and specifically is an NPN transistor because the junctions are set up in negative, positive, negative order. The terminals of a BJT transistors are called collector, base, and emitter. To avoid getting drowned in details, it's good to have models that are rough approximations. So we can think of a BJT transistor as a current amplifier. The current flowing into the base is multiplied as the current that flows into the collector. And that simple model will take us a long way. In this case, it's pretty easy to analyze what's going on because we're only feeding it a square wave into it. So the input is either going to be low or high. So let's have a look at what happens when the input is low. In that case, the base is at 0 volts and no current flows from the base to the emitter, which is also our ground. When we multiply 0 by some factor, we get, yes, 0. So no current flows into the collector, which means that there isn't much of a voltage drop across the resistor and the output is 5 volts. When the input is high, the base has a positive voltage drop. At that point, current starts flowing from the base to the emitter, and because of that junction is somewhat like a diode and the emitter is tied to ground, the base will remain at about 0.6 volts. Now, a lot of current is flowing into the collector, which makes a significant voltage drop across the 100 ohm resistor, and that makes the output voltage drop down to pretty much zero. So really what this transistor is doing is inverting the clock signal generated by the gate array. I had initially speculated that it was boosting the signal because maybe it was too weak, but I think that's completely wrong. I can't imagine this clock signal is going to have a lot of current draw going into the Z80, so it could have been fed from the gate array directly just fine. Also, it's not that the signal needs to be squared off because I think it's plenty square coming from the gate array, so it's just inverting it. So why didn't they generate it inverted in the gate array in the first place? That's beyond me. I'm sure they had a couple of spare transistors there, so maybe this is more of a fix that they applied after the gate array design was completed? I'm not sure. To reinforce our understanding of what's happening, I decided to enter this circuit in an online simulator. Just the clock signal, a transistor, and a couple of resistors. We're plotting the input voltage of the clock signal and the output voltage. And yes, here it is. It also shows that it's a perfect inverter. Now, this isn't using this exact transistor model, and it's all very rough and idealized. So let's set up a similar situation with real transistors to see if they behave that way in real life. I'm going to connect one probe to the base of the transistor, that will be channel 1 in yellow. The other probe to the collector, which is the output signal and will be channel 2 in blue. What we're seeing here is the clock signal out of the gate array. Normally it would have an amplitude of 4 or 5 volts, but here it's already being fed into the base of the existing transistor. And as we saw before, there's only a voltage drop due to the junction of the transistor, and that's why the signal right now is under 1 volt. On the second channel, we have the output signal at the collector of the transistor. And yes, that's exactly what we expected again. The signal is inverted and it reaches a bit over 4 volts. It also looks very nice and square. So yes, that looks a lot like what we had deduced by looking at the circuit, and it's also quite similar to what we saw in the simulator. Now let's try to build a similar circuit from the ground up on a breadboard so we can run some experiments and see the effect that different transistors have. The original transistor was a ZTX312, which isn't manufactured anymore. That's the original problem. The ones I'm going to be experimenting with are the BC547, the 2N2369, and the MOSFET 2N7000. They're all in production and you can buy them new without any problems. We'll start really simple and work our way up. Here we have a transistor set up in a very similar way to the Amstrad. We have a 100 ohm resistor at the collector and the emitter is tied to ground. And the base itself is connected to this button. When the button is not pressed, there are 0 volts at the base, and when we press the button, we give it 5 volts. So the button will be kind of our clock signal with the advantage that we get to control it to see what's going on. The specific transistor we have here is the BC547, which is very common and easily available NPN transistor. I would love to be able to use this to replace the weird one on the Amstrad board. So, like before, channel 1 is going to be the input, which is whatever we're sending with the button press, and channel 2, in blue, is going to be the output, which is the collector of the transistor. And as soon as I power it on, we get exactly what we expected, 0 volts input and pretty much 5 volts output. And when I press the button, input goes high and output drops down very low. Excellent. Okay, so the next step is to change the button by a real square wave. I consider setting up a crystal oscillator and then some gates to shape the square signal, but in the end, I decided to go old school and set up a simple 555 timer. You really can't beat the simplicity of a small chip like that. And when I turned that on, perfect. Again, input square wave and output is a similar square wave, but inverted. So does this mean that we can just go ahead and use this on the Amstrad? Not quite. We're sending a square wave to the transistor, but it's really slow. This is only about 470 Hz, and on the Amstrad it's going to be 4 MHz, which is almost 10,000 times faster. The 555 timer can't create a 5 MHz wave, but it can definitely go a lot faster. I believe it can reach about 500 kHz. So we can do that by changing the timing capacitor to something much smaller. Here I have changed it to 33 picofarads, and yes, that's a lot faster. That's over 300 kHz. However, notice that the waves aren't quite as square anymore. The input wave has a spike in it at the beginning, but that's just part of the 555 timer and some capacitance, so I'm not too concerned about that. I'm concerned about the shape of the output wave, the blue one. The duty cycle of the output wave looks off, and with the low period being much longer than the high period, and the edges aren't even sharp, straight transitions the way they should be. Uh-oh. It turns out we can improve the edge transitions by putting an adjustable resistor at the base to limit the current flowing through the transistor just to the right amount. And when we do that, the transitions are much better. but that's not solving the other problem. I can also tweak the resistance into the collector itself, and that again improves things, but it's not perfect. Now the transitions are better. We can see that as soon as the input signal rises, the output goes low, which is what we want. And that's very quick. But when the input transitions to low again, there's a bit of a gap before the output goes high again. It looks like the transistor is taking a while to switch off the current flow from the collector to the emitter. This might not seem like much, but remember that we're only running at about 300 kilohertz. Once we go to the full megahertz, I'd hate to see what that delay looks like. Actually, we are gonna see it in a bit. To tell you the truth, I was pretty puzzled at this point. From reading through the BC547 datasheet and some of the research I had done online, I expected the transistor to work perfectly fine in the megahertz range, so it was really surprising to see it acting so sluggish at such low frequency. The datasheet doesn't list specific switch on or off times, but it lists the current gain bandwidth product as being 300. That means that at 1 megahertz it can have 300 times gain, and all the way at 300 megahertz it doesn't gain anything and it's just 1-to-1. So clearly we should not be struggling at 300 kilohertz. This is probably where I spent the longest amount of time. I was not happy to have my experiments come up with very different results than what I was expecting from my understanding of this transistor. So I dug into my favorite electronic books, The Art of Electronics, and I reread all the relevant sections I could find, but there was nothing about this. Online, I kept finding comments about some people saying that the BC547 transistors could switch on and off really fast, and some other people saying that they didn't. So clearly, there was something going on in here, and I wasn't the only one confused. It was then that Marcus on the Discord channel pointed me to a website discussing this exact same topic. It turns out that when a BJT transistor is turned on and it's fully saturated, it has some charge stored in the base area. When the voltage changes at the base, that charge is still there, and it continues to make the current flow from the collector to the emitter until it's fully used up. That's exactly the delay we're seeing. In case you're gonna go research this, this is also called the Miller effect. So how do we fix it? We would need to add something so when the voltage drops at the base, it sucks away all those electrons at the base region really quickly. We can accomplish exactly that by adding a capacitor. This is a well-known technique to speed up off transitions of BJT transistors, and it even has a name, the speed-up capacitor. There's another technique called a Baker clamp involving a diode, but you can read about that by yourself for extra credit. One thing that was extra frustrating is that the Art of Electronics 2nd edition has a whole section dedicated exactly to this, even with oscilloscope traces showing the exact problem and discussing different solutions. Unfortunately, that chapter was removed in the 3rd edition, which is the one I have here. I guess that was considered to be all the stuff that is not very applicable to modern electronics. So the lesson there is, don't dismiss an electronics book just because it's older. Sometimes it'll have even more relevant information to the kind of things we do with these old computers. Okay, enough of that. Let's try it. Could it really be this simple? To see if it really makes a difference, I've added the capacitor across the resistor, but it's not fully hooked up yet. To close the circuit, I need to connect that orange wire. So with it off, we see the ugly blue signal just like before, and then when I connect the orange wire, well, the output signal seems to happen right away without a delay, but now the input signal looks kind of messed up. But by adjusting the base resistor to tweak the input current, oh, look at that. That looks perfect. We have a perfect square wave for output. And just to check, if I unplug the wire, yep, it looks messed up again. I put it back, boom, perfect output. That speed-up capacitor really worked. And this is a perfect example of why transistor replacement tables don't always work. Unless you know what parameters really matter for your very specific circuit, you may end up with a transistor that is 99% the same, but somehow has slow switch-off characteristics, and it will fail without making extra modifications. Before taking all of this and putting it on the Amstrad board, I want to run some tests with 2 other transistors. The first one is called 2N2369 and has this funky rounded body that I hadn't seen before. Someone in the comments suggested that this was a really fast transistor and it might be a good replacement for the original one. Since I had a few spare ones because it's present in the Dragon 32, let's see how it behaves in this setup. And with this one, wow, it's just a matter of turning it on and instantly we get a perfect inverted square wave. It looks like this one is a perfect match for the original transistor as far as this circuit is concerned. Finally, I wanted to try the same thing with a 2N7000 transistor. This one is pretty different because it's a MOSFET instead of a BJT, so it has a pretty different behavior. In particular, this kind of transistor builds up less charge, so in theory, it should be able to switch on and off much faster than the BJT ones. MOSFET transistors are different enough that their terminals even have different names and symbols. So instead of collector, base, and emitter, we have source, gate, and drain. So I double-checked the datasheet to make sure that I had the correct orientation, and I added it to our simple circuit. And when I turn it on, ooh, what's going on in here? When the input is high, the output is low. But when our input is low, the output is barely high at all. It looks like it's under half a volt, and it's not even something that I can adjust with the resistances. So I puzzled this one out for a while, and I ran some more tests, but the transistor just wasn't working the way I expected it to. I actually could have left this out of the video completely and moved on, but that's actually not fun. The following day, I was looking for more specific speed parameters in the datasheet, so I got the datasheet for the same model but from a different manufacturer. And there I saw this. The source and drain are reversed in the two data sheets. What? So I flipped the transistor and what do you know? It works like a champ. And it looks like it doesn't need any extra resistances either, so it could fit perfectly on the CPC board without any modifications. Well, on the plus side, now I know that plugging in this transistor backwards doesn't make it explode. So what happened here? Is it really possible that two manufacturers will create the same transistor model but with different pinouts? At first I thought that this must be the case and it was just crazy, but then I was told that this is not the first time that OnSemi has incorrect data sheets, so that feels a lot more palatable than having different pinouts for the same model. So hopefully that's the explanation. Okay, so now it's time to take all this knowledge and put it back into practice to accomplish our original goal, to replace the clock signal transistor on the Amstrad CPC board. I want to try the transistors with the Amstrad, but I don't want to solder and unsolder them all, so I'm going to feed the signal from the gate array into our breadboard directly. I'll just carefully bend pin 39 so it doesn't connect to the rest of the board, and we can send that signal to our transistor inverter. We'll start with the BC547 just like before. Initially, the signal looks pretty horrible, so I have to adjust the resistances at the base and the collector. If we knew exactly how much current the gate array can provide, this is a place where we can actually use some accurate equations and try to derive the ideal resistor values. But here, I'll just tweak them until they look good. And yeah, that output wave looks pretty good now. Also, just to check, if I remove the speed up capacitor, yeah, look at that, wow. The output becomes pretty much flat because the transistor doesn't even have time to react. Interesting. Okay, on to the 2N2369. This one also looks rather ugly with the resistor set from the last transistor. But when I set the adjustable transistors down to 0, the output wave looks perfect. So this is really encouraging. And finally, the 2N7000 MOSFET. After a little bit of tweaking, the output wave is not bad, but it's not as square as the previous transistor. It's not fantastic, but it may be good enough. But one thing is working on a breadboard, and another one is working on the real computer at a full 4 MHz, so let's add it to the board and see. We could definitely get the BC547 to work, but it would require at least one extra resistor and one capacitor. And I'm sure we could put those on the underside, but it would just look a bit ugly. A tidier approach would be to use one of the other two transistors since they don't need any extra components. I'll pick the 2N7000 because it's the most common of the two transistors. And with the MOSFET transistor in place, oh, that square wave doesn't look quite right. So it looks like we need to adjust some of the resistors to get a perfect square wave like we saw on the breadboard. So we could do that, but then we would have to modify other components beyond the transistor itself, so that could get a little confusing for the bill of materials of this replacement board. So instead of that, let's try the other transistor and see if it just works straight. Okay, and with the other replacement transistor, we turn it on and oh yeah, look at that. That is perfect. We get the perfect square wave, inverted, and perfect edges. So yeah, I think this is the perfect replacement transistor. Just to make sure, let's see the computer actually running. And yeah, that seems to work great. There are a couple interesting things worth talking about in this particular circuit. One of them is that it looks a little weird to have the transistor without a resistor at the base to limit the current. Because in a way, when the transistor gets turned on, it pretty much shorts the base to the emitter, which is a ground. But when you look closer at the schematics, you see that on pin 39 of the gate array, it says that it's using a passive pull-up. So that makes a lot of sense, because it's wired directly to VCC with some kind of large resistor. So when it goes high, that resistor is the current limiting resistor that prevents a short to ground. The other interesting bit is that if you look at the next revision of this board, this transistor is completely gone. Of course, the CPU can't receive a non-inverted clock signal because that's crucial for the coordination of the gate array and the CPU. So instead, later designs changed the chip used in the clock signal squaring with the oscillator from 4 NAND gates to 6 inverter gates. So they use one of the spare inverter gates to invert the clock signal and send it to the CPU. That makes a lot more sense than having a spare transistor in the board, so I wonder why it wasn't done that way from the start. Maybe it was a routing issue since the signal needs to move away from the CPU a bit and then travel back to the CPU? I'm not really sure, but certainly the second revision makes a lot more sense. And so there you have it. The moral of all of this is that finding a good transistor equivalent isn't trivial, and it's worth taking the time to understand how exactly it's going to be used. Obviously, doing this with every transistor is exhausting, but once someone does it, hopefully it goes in the bill of materials for the project and everybody can safely use that. Anyway, I hope you enjoyed this video. I certainly learned new things while I was investigating all of this, so I always enjoy that. Thanks to all of you who helped along the way with your comments and suggestions, and I'll see you next time. If you enjoyed this video, please consider supporting Noel's Retrolab on Patreon or joining the membership on YouTube. Not only is that the best way to support this channel and allow me to continue making more videos, but you also get some extra perks like early access, ad-free videos, and more. Thank you again to all the supporters. See you next time.